do you actually exist right now at this exact fleeting moment?
Right. Or are you just a four-dimensional slice of a massive solid space-time worm?
Exactly. And if time really is just, another dimension, completely no different from up, down, left, or right,
Then why on earth don't you remember the future the exact same way you remember the past?
it's the ultimate philosophical vertigo, honestly. I mean, we navigate our entire lives based on this unshakable gut feeling that you, the listener, feel right now.
Yeah, the past is dead and gone, the present is the only thing that's real, and the future is just this open frontier waiting to be written.
But the terrifying thing is, well, when you apply the cold, hard mathematics of modern physics to that deeply human feeling, the entire structure of reality just starts to crack.
It shatters, actually. I mean, it completely falls apart.
And to try and put those pieces back together, today we are taking a massive deep dive into a really heavy source. We're tearing into the Oxford Handbook of Philosophy of Time.
Yeah, this is an absolute titan of a book. It's edited by Craig Callender, and it sits right at the bleeding edge where hardcore fundamental physics collides with abstract metaphysics.
Right, and it is definitely not a light read. The mission for today's deep dive is to completely dismantle our intuitive, everyday experience of the clock ticking on the wall.
We really have to replace that intuition with something far more bizarre. I mean, we're going to cover everything from Einstein and thermodynamics to, quantum gravity and the ethics of human mortality.
Which is exactly what makes this subject so intoxicating, because by the time we finish this discussion, your baseline reality is going to be radically altered.
Oh, absolutely. The way you experience the passing of a second, or even the way you view your own mortality, it's all going to shift.
The universe is just infinitely weirder than a simple ticking clock. So, I mean, to figure out how we exist in time, we first have to figure out what time actually is in the physical universe.
Right. And that means we have to start with the great dictator of classical reality, Isaac Newton.
Yeah, so we're jumping into the book's breakdown of classical dynamics, specifically Lawrence Sklar's analysis of Newton's famous Principia.
Sklar points us right to the scholium, to the definitions, where Newton drops this absolutely massive claim about reality.
Yeah, the quote is, "Absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external."
And that sentence right there, well, that's the bedrock of the world as we intuitively understand it.
Right.
Newton is making a staggering ontological claim. He's saying that time isn't just a convenient human invention for, measuring how long it takes an apple to fall from a tree.
He is arguing that time is a physical, independent structure of the universe, like it exists entirely on its own.
Exactly. It's a real thing, independent of the stuff inside the universe.
The way I always picture Newton's concept of absolute time is like a giant, indestructible metronome sitting in the empty void of space. It's just tick, 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 tick.
That is a perfect visual.
Right, like it doesn't care about the stars, it doesn't care about the planets, it doesn't care about humanity. You could wipe out all the matter in the entire cosmos, leaving nothing but empty space, and that metronome would still be ticking at the exact same rate.
It's a great analogy, but what's crucial to understand here is why Newton built that metronome into his physics in the first place.
Right, he wasn't just trying to be poetic.
No, not at all. He was backed into a mathematical corner.
Yeah.
To make classical dynamics work, to actually write down the laws of motion and universal gravitation, Newton needed a fixed, unmoving backdrop.
Because you need something to measure against, right?
Exactly. Think about it. If you want to measure the true objective acceleration of two comets hurtling toward each other, you need an absolute standard of change to measure them against.
You need a rigid ruler for space and an unbending clock for time.
Yes. Without that absolute background, the math of classical mechanics completely falls apart. You can't calculate force or mass without a universal clock.
But that beautiful, simple, intuitive metronome just didn't last. Because a couple of centuries later, Albert Einstein shows up, takes Newton's rigid universal clock, and completely smashes it into pieces.
He really did. And the handbook explores this massive shift through Stephen Savitt's analysis of special relativity.
Yeah, Savitt pulls a quote from Einstein reflecting on his own work in 1949, where Einstein says, flat out, there is no such thing as simultaneity of distant events.
And with that one realization, the Newtonian universe is just dead.
Wait, hold on, I have to push back here, because this is where the average person's brain, including mine, starts to reject the premise.
That's deeply unintuitive, yeah.
If there is no simultaneous now across the universe, doesn't that break our entire fundamental grip on reality?
It definitely shatters the illusion of a shared reality.
Right. Because if a supernova explodes in a galaxy a billion light years away, I desperately want to be able to point up at the sky and say, that star is exploding right now. But Einstein is saying now doesn't actually exist out there.
That's exactly what he's saying. And the how of it is what makes special relativity so brilliant.
Okay, break that down for me.
The core mechanism here is the speed of light. Einstein realized that the speed of light is the absolute speed limit of the universe, and it is perfectly constant for every single observer.
No matter how fast they are moving, right?
Right, exactly. But to keep the speed of light constant, something else has to give. You can't just have an absolute speed limit without the environment reacting. And what gives is space and time themselves. They have to stretch and squish.
Oh, right. The famous time dilation.
Yes, time dilation and length contraction. So imagine you and I are trying to determine if two lightning strikes, let's say one in New York and one in London, happened at the exact same time.
Okay, I'm picturing it.
If you are standing perfectly still on Earth, right in the middle of the Atlantic Ocean, the light from both strikes reaches you at the exact same moment. So you declare they were simultaneous.
Right, that makes total sense from my perspective.
But if I am flying past you in a spaceship at half the speed of light, headed toward London, I am flying into the light from the London strike and away from the light of the New York strike.
Ah, so the light from London hits your eyes first.
Exactly. So I declare definitively, based on physical evidence, that the London strike happened before the New York strike.
And the mind-bending part is that neither of us is wrong. Mine now, where they happen together, is just as physically valid as your now, where they happen sequentially.
Precisely. This is what physicists call the relativity of simultaneity. Time transforms from an invisible, rigid stage into a flexible, dynamic participant.
It gets woven together with the 3 dimensions of space into a 4-dimensional fabric, right? Space-time.
Exactly. Space-time, your timeline, your personal now, is inextricably linked to your velocity. There is no universal master clock.
So the universal clock is gone, and time is just this local, personal experience smeared across a 4D space-time fabric. But that immediately forces a completely wild question.
Which is,
If the universe is this massive, smeared-out space-time block, how do we physically exist inside it? Are we just 3D objects writing a timeline, or are we something weirder?
and that plunges us right into the metaphysics of existence, specifically Yuri Belashov's deep dive on persistence.
Right. How do things actually persist from one moment to the next?
Belashov breaks this down into 2 warring metaphysical camps. You have endurantism, which is often called 3dism, and perdurantism, which is known as 4dism.
And these aren't just like minor disagreements. These are fundamentally opposite ways of defining what a physical object actually is.
Absolutely. They change the entire definition of what you are.
Okay, let's use a visual to separate these 2 camps. Let's imagine human existence as bread.
Okay, I like where this is going.
If you belong to the endurantism camp, the 3dism camp, you view yourself like a single slice of bread moving down a conveyor belt of time.
Right, so you are wholly present at every single moment you exist.
Yes. The you sitting here today is 100% of the you that exists. There's no part of you left behind in yesterday.
And that's the view almost everyone intuitively holds. It's common sense.
Right, but then there's the perdurantism camp, the 4D view. In this view, you aren't the moving slice. You are the entire, solid, baked loaf of bread stretching from the exact hospital bed where you were born to the exact spot where you'll eventually die.
It's a massive shift in perspective.
Yeah, and the you that is listening to this right now, that's just one tiny cross-sectional slice of the whole loaf. You are a massive 4-dimensional worm made up of billions of temporal parts.
It's an incredibly vivid analogy. But, why would philosophers invent the 4D loaf of bread? It sounds insane.
It really does. It sounds like sci-fi.
They do it because the 3D moving slice, as intuitive as it feels, crashes headfirst into a massive logical wall. It's called the problem of temporary intrinsics.
Oh, okay. Walk me through that.
Let me try to break it down. If you are wholly present on Monday and you are sitting down, you possess the intrinsic property of sitting.
Makes sense.
But if you are wholly present on Tuesday and you are standing up, you possess the property of standing. But how can the exact same 100% wholly present object possess entirely incompatible properties? You can't be both sitting and standing.
I mean, my instinct is just to say, well, because it's happening at different times.
But if the object is truly wholly present, the time shouldn't matter to its core intrinsic nature.
Oh, I see.
So the 4D Perdurantist steps in and says, we can solve this easily. They say it's not the whole you that is sitting on Monday and standing on Tuesday.
It is your Monday temporal part that sits and your Tuesday temporal part that stands.
Exactly. There is no logical contradiction, just like there's no contradiction in your left hand holding a cup of coffee while your right hand is empty. They are just different parts of the same whole object.
That does make logical sense, but man, it introduces a whole new set of headaches.
Oh, definitely.
The Handbook highlights the philosopher Theodore Sider, who points out how complicated this gets when you talk about motion or cause and effect.
Right. Motion becomes very strange in 4D.
Because if I throw a baseball and it shatters a window, in the 4D view, a solid, static baseball worm just exists in a space-time geometry where its later temporal parts physically intersect with a static, shattered window worm.
Yes, Fordism forces us to entirely redefine what motion and location even mean. Things don't really move. Their worms just bend and intersect.
Wild.
But here's the kicker, and why a lot of physicists lean heavily toward Fordism. It plays incredibly well with Einstein.
Ah, right, because of relativity.
Exactly. In a relativistic universe where my now is different from your now, the idea of a 3D object being wholly present at a specific moment starts to break down. We can't even agree on what the present moment is.
So the moving slice gets all warped and confusing.
Right. But if objects are just solid four-dimensional volumes embedded in space-time geometry, relativity doesn't break them. They just look like different cross-sections depending on the angle or the speed from which you slice them.
Which leads to a deeply unsettling thought. I mean, if the 4D view is right, and we are just static space-time worms stretching from birth to death, that implies the future's already out there.
Yeah, it's already baked into the loaf.
So what if I refuse to accept that? What if I demand that only the now is real? That brings us to Dean Zimmerman's fierce defense of presentism in the book.
Presentism is the ultimate common-sense philosophy.
Right. It states the past is completely gone, the future doesn't exist yet, and reality is only the razor-thin, bleeding edge of the now.
It's a comforting thought. It preserves our feeling of free will and an open future.
But wait, how does Zimmerman actually defend presentism against special relativity?
Yeah.
We literally just established that Einstein proved simultaneity is relative.
It is a massive hurdle for presentists.
If you fly past me in a spaceship, your now includes events that are in my future, and my now includes events that are in your past. So if presentism says that only the now actually exists, whose now is the real one?
That is the big question.
Does the universe physically pop into existence differently for me than it does for you? That sounds completely absurd.
It is the absolute crucible for presentism, and Zimmerman really has to sweat to find a theoretical escape hatch here.
So what's his escape hatch?
To save the idea that only the present exists in a relativistic universe, a presentist essentially has to bite a massive bullet. They have to argue against the standard interpretation of Einstein.
Wow, going against Einstein is bold.
They have to argue that even though our clocks and our math are relative, there must be a privileged, hidden, absolute reference frame in the universe, a master clock.
Wait, a return to Newton's metronome, but where would they even find that in modern physics?
Well, they look for cosmic anchors. Some presentists point to the cosmic microwave background radiation.
The residual heat left over from the Big Bang, right?
Exactly, that heat that fills the entire universe. They argue that if you align yourself perfectly with that background radiation so it looks uniform in all directions, you have found the universe's ultimate objective rest frame.
Oh, I see. And whatever now exists in that frame is the true metaphysical present.
Yes. Now, it's highly controversial, and a lot of physicists hate it because it adds a clunky, invisible metaphysical structure that the math of relativity doesn't actually need.
Right. It feels like shoehorning an old idea into new physics.
But Zimmerman maps out how you can logically defend it if you are desperate to save the reality of a moving present.
But let's play devil's advocate for a second. Let's say Zimmerman is wrong. Let's say the 4D block universe is real, the master clock is a myth, and the future is already fully written.
Okay, entering the block universe.
That brings us to Craig Bourne's chapter on fatalism, and this is where the philosophy of time collides directly with pure logic. Bourne revives this incredible ancient problem from Aristotle's De Interpretation 9.
Right. It's known as the sea battle paradox. It's one of the most elegant and frustrating thought experiments in philosophical history.
Okay, so Aristotle says, imagine I stand on the beach today and I confidently declare there will be a massive sea battle tomorrow. Now, Aristotle asks a deceptively simple question. Is my statement true today?
And this seemingly innocent question threatens to destroy the entire concept of free will.
How so?
Because classical logic operates on the law of excluded middle. Every single statement must be either 100% true or 100% false. There is no middle ground.
So if the statement, there will be a sea battle tomorrow, is already true today, then the future is entirely fixed. Fatalism is real.
Exactly. The admirals don't have to bother planning tactics. The sailors don't have to worry about their armor. The outcome is literally locked into the logical fabric of the universe.
The universe is just waiting for the clock to catch up to a truth that already exists.
Yeah, that's exactly how classical logic frames it.
I hate that. I really want the future to be undetermined. So how do logicians fight back against Aristotle?
They do it by fundamentally breaking classical logic.
That sounds drastic.
It is. Born walks us through the work of the Polish logician Jan Łukasiewicz, who was so disturbed by this fatalism that he developed a multi-valued logic. He looked at the law of excluded middle and just threw it out.
So he just refused to play by the rules.
Yeah, he introduced a third truth value, indeterminate.
So he literally invented a wait-and-see category for logic.
Yes, he built these incredibly complex truth tables, which the handbook actually details with figures, to show how math and language can function if statements about the future are neither true nor false.
So there will be a sea battle tomorrow is simply graded as indeterminate.
Exactly.
That feels like a clean fix.
You'd think so, but Łukasiewicz's tables created a massive philosophical uproar.
Why? What broke?
Let's say I make a compound statement. I say, there will be a sea battle tomorrow, or there will not be a sea battle tomorrow. In Łukasiewicz's system, because both halves of that sentence are indeterminate, the entire sentence is graded as indeterminate.
Oh, wait. I see the problem. A or not A is a tautology. It has to be true. Either the battle happens or it doesn't. There's no third option in reality.
Right. Most philosophers felt that saying it will rain tomorrow or it won't rain tomorrow is a guaranteed truth, regardless of what the weather actually does.
It's logically bulletproof even if we don't know the outcome yet.
Exactly. So the handbook also brings in Michael Dummett, who tries to solve this by separating the concept of truth from the concept of evidence.
How does he separate them?
Dummett asks, can a statement be true today, even if the physical evidence for its truth hasn't happened yet? It shows how our very rules of logic contort and strain when they try to map onto a timeline that hasn't happened yet.
And while we're talking about the fundamental fabric of time straining and breaking, we absolutely have to touch on Jean-Paul Van Benegim's chapter.
Oh, this one gets incredibly granular.
Yeah, he asks a question that sounds like it belongs in a computer science class, not physics. Is time a continuous, infinitely divisible flow, or is it discrete?
Right, like, is the universe running on a frame rate, like a video game or a movie reel? Is time pixelated?
This is the battle between continuous mathematics and discrete geometry. If time is continuous, you can zoom in forever. A second can be cut into a millisecond, then a microsecond, infinitely down.
But if you can infinitely divide time, you run straight into Zeno's paradoxes.
Oh, I remember Zeno. He said that if you want to walk from your chair to the door, you first have to walk halfway there.
Then you have to walk half the remaining distance.
Yeah.
Then half of that.
Right. And if space and time are infinitely divisible, there are an infinite number of halfway points, which means it should mathematically take you an infinite amount of time to cross the room. You should never be able to reach the door.
But we obviously do reach the door. So Van Benegim analyzes the alternative. What if time is discrete?
What if time is made of tiny, indivisible, fundamental pixels? I think they're called chronons.
Yes, chronons. If time is pixelated, Zeno's paradox just vanishes. You don't have infinite halfway points. You just teleport from one pixel to the next, frame by frame, like Mario moving across the screen.
But the moment you pixelate time, you get hit with what I instantly recognize as the Kantian paradox.
And what's the Kantian paradox?
Well, if time is made of discrete blocks, then there must have been a very first block, a first frame of reality. But the human mind physically cannot comprehend a boundary to time because we inherently ask what came before the first pixel.
Our brains just refuse to accept a hard start date for reality.
Or even weirder, how does the universe mechanically step from the first pixel to the second without there being a moment between the pixels?
That's the nightmare of discrete geometry. Van Benegim details how incredibly difficult it is to make physics work on a grid. How do you model smooth, curved acceleration when reality is made of rigid, square blocks?
Right, it feels too jagged for the real world.
More importantly, how do special relativity's Lorentz transformations, which squish and stretch time based on velocity, work if time is made of indivisible, unsquishable pixels?
The Kantian paradox really just proves the limits of our cognitive architecture. Whenever we try to place a boundary on reality, our brains just crash.
They absolutely do.
All right, so time might be a solid 4D block. It might be an open present. It might be infinitely smooth, or it might be a pixelated video game. But amidst all of this high-level theoretical weirdness, there is one brutally physical fact that we cannot deny.
And that is?
We experience time moving in one strict, undeniable direction.
The arrow of time.
Exactly. We can scramble an egg, but we can't unscramble it. We remember the past, but we have absolutely zero memory of the future. Why?
This pulls us into part 4 of the book, the direction of time and the incredibly heavy realm of thermodynamics.
We start with Douglas Kutak's chapter, and a concept so contrarian is literally called Ehrman's heresy.
Named after the brilliant philosopher of physics John Ehrman, and championed aggressively in this text by Tim Maudlin.
When I first read about Ehrman's heresy, my jaw literally dropped. Ehrman essentially looks at the universe and declares that the direction of time, the arrow of time pointing from past to future, is a total illusion.
He says it doesn't fundamentally exist.
Which sounds like absolute madness. I mean, if you drop a wine glass on a tile floor, it shatters into 100 pieces. Those shards never, ever spontaneously jump back up off the floor and seamlessly reassemble into a perfect glass in your hand.
Never.
So how can Ehrman claim the arrow of time isn't real?
He claims it because he actually looked at the foundational equations of physics. And this is the great dirty secret of fundamental physics. Almost all the laws governing the universe are perfectly time-symmetric.
The math works both ways.
Yes. Look at Newton's laws of motion. Look at Maxwell's equations for electromagnetism. Look at quantum mechanics. The math simply does not care which way the clock ticks.
Right, the reverse movie analogy.
Exactly. If you film 2 billiard balls colliding on a pool table, and then you play the movie backward, the backward footage still perfectly obeys every single law of physics.
Right, momentum is still conserved.
If you showed the reversed footage to a physicist, they wouldn't be able to point to a single broken equation to prove the film was running in reverse. At the fundamental particle level, the past and the future are identical.
So the philosophers Reichenbach and Gold, who are analyzed in this section, what do they actually do with this massive contradiction?
They looked at this microscopic symmetry and argued that the flow of time from past to future has no physical basis in the fundamental laws. Our feeling of a moving timeline might just be a local artifact, a macroscopic trick.
Ehrman's heresy strips the arrow of time of its fundamental reality.
It really does. It says the arrow is a human imposition.
But wait, the fundamental particles might not care about time? But I am not a fundamental particle. I am a complex human being, and the wine glass still shatters, and the egg still scrambles.
Right. The macro world is messy.
If the foundational laws of physics don't provide an arrow of time, what the hell does? This perfectly sets up Jill North's incredibly dense chapter on thermodynamics.
This is where we have to abandon the behavior of single particles and zoom out to look at massive systems of billions of particles. This is statistical mechanics.
Okay, so North unpacks the framework laid out by physicist David Albert, right?
Yes. Albert says that to explain why the egg breaks and doesn't unbreak, you need 3 ingredients: the fundamental dynamic equations of physics, a statistical postulate, and the absolute linchpin of our reality, the past hypothesis.
Okay, let's break this down. Let's explain the past hypothesis like I'm 5, because this is where physics starts sounding like magic.
To understand the past hypothesis, you first have to understand entropy.
The second law of thermodynamics.
Exactly. It states that in a closed system, entropy, which is essentially a measure of disorder or randomness, always increases. A highly ordered state, like a pristine, uncracked egg, will naturally evolve into a disordered, high-entropy state, like a scrambled mess.
Why does it always go that way?
Simply because there are astronomically more ways for a system to be messy than for it to be ordered.
Right. There is only one way to arrange the atoms to make a perfect wine glass. There are trillions of ways to arrange the atoms to make a pile of shattered glass on the floor.
Exactly. But here's the horrifying problem that statistical mechanics reveals. Because the fundamental laws of physics are time-symmetric, statistical mechanics tells us that a system should evolve into high entropy in both directions of time, past and future.
This is the part that completely broke my brain. Give me the ice cube example.
Okay, let's say you walk into a room and find a glass of water on a table, and floating in the water is a half-melted ice cube. That is a medium entropy state.
Okay, got it.
Now, if you use statistical mechanics to predict the future, it tells you the ice cube will melt, the water will reach room temperature, and entropy will increase. That perfectly matches our experience.
Right, nothing weird there.
But if you use statistical mechanics to retrodict the past, to guess what the glass looked like an hour ago, The math tells you that an hour ago it was also a puddle of lukewarm water, and by sheer random statistical fluctuation, the water molecules magically arranged themselves into a half-melted ice cube right before you walked in.
Which is completely insane. Every ounce of common sense tells me that an hour ago it was a fully solid ice cube fresh out of the freezer, a low entropy state.
But the math says it's infinitely more probable that the ice cube spontaneously assembled out of a puddle than it is that it started as a solid cube.
Yes, because a fully solid ice cube is a state of incredibly low entropy, and low entropy is statistically highly improbable.
So, to prevent all of our memories and all of our history from being erased by statistical mechanics, David Albert introduces the past hypothesis.
He forces a fix.
He says we must brutally force a new rule into the universe. We must declare, as a fundamental law of nature, that the universe began in a state of spectacularly, uniquely low entropy.
We call this the Big Bang, a dense, hot, incredibly ordered singularity.
Exactly. The ultimate low-entropy starting gun.
So the only reason the arrow of time exists, the only reason we remember yesterday but not tomorrow, the only reason the glass shatters and doesn't unshatter, is because the entire universe is essentially a wound-up clock that has been slowly winding down for 14 billion years.
That is precisely what the past hypothesis dictates. Time's arrow is just the universe sliding down a massive thermodynamic hill toward total chaos. We are just surfing the gradient of entropy.
But the book doesn't let us off the hook that easily. It brings up Ludwig Boltzmann, the father of statistical mechanics, and his challenge is pure nightmare fuel.
Oh, the Boltzmann brain.
Boltzmann realized that if the universe is infinite and it exists forever, eventually it will reach the bottom of that hill. Maximum entropy. A featureless dead soup of perfectly distributed particles where nothing ever happens. Heat death.
But eternity is a very long time.
Right. Boltzmann realized that in an infinite amount of time, random statistical fluctuations must occur. In this dead soup, particles will randomly bump into each other. Eventually, a group of particles will randomly bump together to form a dust cloud. Wait long enough, particles will randomly bump together to form a star.
Which leads to the most unsettling philosophical consequence in modern physics.
The Boltzmann brain. Because mathematically, a smaller, simpler fluctuation is infinitely more likely to happen than a massive, complex one like a whole universe.
The math on this is brutal.
So it is mathematically vastly more probable that out of this dead, infinite soup, particles randomly bump together to form a single, fully functioning human brain, complete with false memories of a childhood, false memories of a solar system, and false memories of listening to a deep dive that exists for exactly 1 second before dissolving back into the void.
It is the ultimate solipsistic dread. It is vastly more likely that you are a spontaneous Boltzmann brain hallucinating reality right now than it is that a 14-billion-year-old universe actually exists.
If we rely entirely on statistical mechanics without cementing the past hypothesis as an absolute law, we have no scientific reason to believe the universe existed 5 minutes ago. We have to desperately cling to the past hypothesis just to trust our own memories.
It's the only way to stay sane in this framework.
Well, I really hope you aren't a hallucination in my void-floating brain, because if you are, I'd like to think my subconscious could dream up a slightly less depressing scenario.
Fair point.
But let's pull back from the dead, infinite soup, and focus on that brain, on human consciousness. Because thermodynamics gives us cold, hard numbers. It gives us entropy gradients and phase spaces.
But human beings don't experience a phase space. We actually feel time passing. We feel the flow.
Exactly. So how does our wet biological cognitive machinery process the now? This takes us into part 5 of the text, time in action, mind, and immediate experience. Barry Dayton's chapter on time, passage, and immediate experience is an absolute masterclass in phenomenology.
Dayton is trying to bridge the gap between the physicist's static block universe and the psychologist's feeling of flowing time.
To explain this, we have to talk about what psychologists call the specious present. And the best way to understand this is through the analogy of hearing a melody.
The melody analogy is crucial.
If time were truly instantaneous, if our consciousness was just a razor-thin, zero-duration mathematical point of now, we could never actually hear a melody. We would only ever experience a single isolated note, just one tone devoid of context.
Right, because the past note would already be gone.
But when you listen to a song, you hear the melody. Why? Because to hear a melody, your brain must somehow retain the previous note, experience the current note, and actively anticipate the next note, all at the exact same time. Our now is thick. It has a temporal width.
What you're outlining is the phenomenology of internal time consciousness. This was originally pioneered by Edmund Husserl, and a handbook modernizes this brilliantly through the work of Rick Grush.
Husserl analyzed that sick now, didn't he?
He did. He said every single moment of human consciousness actually consists of three overlapping layers. First, the primal impression. That's the raw, immediate sensory data of the exact millisecond.
The note hitting your ear right now.
Exactly. Second, the retention. Grush describes this like a comet's tail. It's the immediate past, still actively vibrating and decaying in your conscious mind. And third, the pretension, which is the brain's subconscious prediction of what's about to happen in the next millisecond.
So our consciousness is basically a constantly updating, smeared-out window of time.
Yes. But Dayton digs into the deep philosophical models of how this window actually maps onto physical reality. He pits extensionalist models against retentionalist models.
Help me understand the difference here, because it gets a little tricky in the book.
It's the difference between actually moving and just looking at a picture of movement.
Okay.
In the extensionalist model, your actual active consciousness physically stretches across time.
Yeah.
The event of you experiencing the world has a literal duration. You are directly perceiving an extended chunk of the timeline.
Okay, so what's the retentionalist view?
In the retentionalist model, the physical act of experiencing is completely instantaneous. It happens in a microscopic, zero-duration mathematical point. But the content of that instantaneous experience contains representations of the past and future.
So it's not stretched out.
No. Think of it like taking a still photograph of a race car. The photograph itself is frozen, but the image is blurred. The blur represents the past motion. Retentionalism says our brains are just snapping instantaneous, blurred photographs that contain memories of a second ago.
So how does this tie back into the physics? If the 4D block universe is real, and the past, present, and future are all just static, frozen chunks of space-time loaf, how do these cognitive models make that static universe feel like it's flowing?
Dayton shows how the brain basically tricks itself. If the universe is a static 4D block, nothing is actually moving or flowing. But along the timeline of your 4D worm, each cross-section of your brain contains a retentionalist snapshot.
Oh, I see.
The brain slice at 12 o'clock contains a short-term memory of 11:59. The brain slice at 12:01 contains a memory of 12.
The universe isn't flowing, but the sequential arrangement of these memory-packed snapshots creates an internal subjective movie.
Exactly. The flow of time isn't out there in the physics. It is an illusion generated entirely by your cognitive architecture, stitching those snapshots together.
Which is a beautiful, if slightly isolating thought. It means the magic of time is entirely inside us.
That's a very internal experience.
But understanding what time is cognitively leads us directly into how we value time emotionally. If the past and the future are equally real in a block universe, why do we care so intensely about the future while we mostly ignore the past?
That transitions us perfectly to part 6, Time and Ethics.
Right. We're looking at David O. Brink's chapter on prospects for temporal neutrality, and Brink reaches way back into history to bring in the ancient Roman philosopher Lucretius.
Lucretius wrote a masterpiece poem called De Rerum Natura, on the nature of things, and within it he tackles the ultimate human anxiety, the fear of death.
Lucretius drops a logic bomb that philosophers have debated for 2,000 years. He writes, "Nature shows us that prenatal non-existence is the mirror image of the time that is to come after we are dead."
This is the bedrock of what's known as the symmetry argument.
So I actually laid out the steps of this argument when I was reading the source. It goes like this. Step 1, death brings complete non-existence. Step 2, the state of non-existence before you were born is identical to the state of non-existence after you die.
They are biologically the same state.
Right. Step 3, you do not feel horror or panic or regret about the 14 billion years of non-existence that occurred before you were born. Therefore, step 4, you have absolutely no logical reason to fear or regret the infinite years of non-existence that will come after your death.
It is a stunning argument. It basically attempts to neutralize the terror of mortality with pure logic. But Brink raises the obvious pushback. The symmetry argument rarely actually comforts anyone.
Right, because humans aren't purely logical.
Exactly. Because human beings possess a profound temporal bias. We are evolutionarily hardwired to care vastly more about the future than the past.
The book gives a great thought experiment for this. Imagine you wake up in a hospital bed with temporary amnesia. A nurse comes in and says, "Good news and bad news." The bad news is, yesterday you had a 10-hour excruciatingly painful surgery without anesthesia. The good news is, the amnesia wiped your memory of it and you are fully cured.
You would feel a massive sense of relief. You'd say, thank goodness that's over.
Yes, that's the philosopher A.N. Pryor's famous observation of our attitude toward past pain. But imagine the nurse comes in and says, good news and bad news. The good news is you feel fine right now. The bad news is tomorrow you were scheduled for a 10-hour excruciatingly painful surgery without anesthesia.
You would be filled with absolute dread and terror.
But why? The total amount of pain in your 4D timeline is exactly the same in both scenarios. One chunk of pain. But we are incredibly biased toward the future.
We care about the surgery tomorrow because we feel we are moving toward it. But Brink weaves in the philosopher Derek Parfit to completely upend how we view our lives and this bias.
Parfit attacks the idea of personal identity, right?
He does. We tend to think of ourselves as a solid, unchanging soul riding the conveyor belt of time. Parfit says no. You are just a chain of psychological connections, memories, beliefs, personality traits, linking the temporal parts of your 4D life.
So the me today is connected to the me of yesterday by strong memories.
Exactly. But as you stretch that timeline, the connections fade. The 80-year-old version of you will have almost no psychological connection to the 5-year-old version of you. They are essentially different people sharing a timeline.
That's kind of sad, but it makes sense.
Parfit and Brink argue that if we view our lives this way, as a loosely connected chain of temporal parts within a block universe, we should strive for temporal neutrality. We should rationally train ourselves to value a happy experience we had a decade ago, just as much as a happy experience we hope to have tomorrow.
Because in the space-time block, both moments exist equally. It's a radical ethical shift that uses hardcore metaphysics to cure human anxiety.
It uses physics as therapy, basically.
Okay, we've covered the metaphysics of bread loaves, the thermodynamics of eggs, the psychology of melodies, and the ethics of death. To finish this massive deep dive, we have to push our understanding of time to the absolute breaking point.
We have to look at the extremes where the equations catch fire.
Part 7. Extremes and Frontiers. Black holes, quantum mechanics, and time machines. Let's start with topology, explored by Jean-Pierre Luminet. He takes the famous twin paradox and makes it even weirder.
Right, the standard twin paradox is the classic intro to special relativity. One twin stays on Earth, the other twin gets in a rocket, flies away at 99% the speed of light, turns around, and comes back.
Because high velocity slows down local time, the rocket twin steps out of the ship having only aged 5 years, while the Earth twin is now an 80-year-old man.
Which is already crazy, but it relies on the rocket physically accelerating and turning around to break the symmetry. Luminet says, what if we don't turn around? What if we change the fundamental shape of the universe itself?
He introduces multiply connected space-time topologies.
This is where geometry gets incredibly fun.
I try to picture this like a classic video game screen, like Pac-Man. If Pac-Man flies off the right side of the screen, he instantly reappears on the left side of the screen.
Exactly.
He never turned around, he just traveled in a straight line through a universe that wraps around itself. Or, in 3D terms, imagine the universe is shaped like a giant donut, a torus.
Luminet mathematically demonstrates that if the universe is multiply connected like a donut, you can fly your rocket in a perfectly straight line, never accelerate, never turn around, and eventually arrive right back at Earth.
But here is the mind blower. When you land, you will find that you and your twin have aged at completely different rates.
Yes. By mathematically calculating the different topological paths taken to the donut, Luminet proves that time isn't just a local artifact of speed. It is etched into the very global geometry of the universe.
And if time is a physical path determined by geometry, the inevitable question arises. Can that path loop back on itself? Can we build a time machine?
Chris Meek in Christian Wuthrich's chapter tackles time travel and the infamous grandfather paradox.
The grandfather paradox is basically the bane of causality. Not that I have a vendetta against my grandfather, but the paradox goes like this. I build a time machine. I travel back to 1920. I accidentally or intentionally run over my grandfather with the DeLorean before my father is conceived.
A classic sci-fi trope.
Because my father is never conceived, I am never born. But if I am never born, I can't build the time machine to go back and run him over. Therefore, he lives. I am born. I build the machine. I go back. And the entire logical structure of the universe collapses into an infinite loop of impossibility.
In physics, these time loops are called closed time-like curves. And the terrifying thing is, general relativity actually allows for them.
Wait, Einstein's math allows time machines?
It does. Solutions to Einstein's equations show that if you have an infinitely long spinning cylinder, or if you fly around a rotating black hole in just the right way, space and time twist so violently that your future path loops smoothly into your own past.
So if the math allows for time machines, how do physicists stop the universe from logically breaking?
Smeek and Woothridge explore several constraints. One of the most famous is the Novikov self-consistency principle. Igor Novikov argued that the laws of physics will simply refuse to allow a paradox to occur.
How does physics refuse a paradox?
If you travel back in time to shoot your grandfather, the universe will actively conspire against you. The gun will magically jam. You will slip on a banana peel. You will miss and shoot the wrong guy. The timeline acts as a self-correcting mechanism to preserve causality.
Which feels like the universe has an intelligence, which I honestly don't love, but there was a footnote in the source material regarding this paradox that absolutely fried my circuits.
Oh, I know what you're talking about.
It suggested we could solve the paradox by abandoning classical logic entirely and using dialectic logic.
That is the most extreme philosophical frontier imaginable.
Walk me through this because it sounds illegal.
Dialectic logic is a paraconsistent logic framework where contradictions can be objectively true simultaneously without destroying the system.
Give me an example of that.
In classical logic, if you say the light switch is completely on A and D, the light switch is completely off, logic explodes. It's impossible. But dialetheism suggests that some paradoxes are true features of reality.
So in the context of time travel,
It means the statements, "you murdered your grandfather," and "you did not murder your grandfather," could both be fully, simultaneously true in the exact same timeline.
that is deeply disturbing.
It is. And because the price of accepting dialectic logic means abandoning everything we understand about reality and truth, physicists desperately prefer to look for geometrical constraints instead. They use concepts like hole freeness in space-time manifolds.
How does hole freeness prevent time travel?
Imagine the universe as a flat sheet of paper. Causality works perfectly. But if you tear a hole in the paper and then take the edges of the hole together to form a tube, you created a shortcut, a time loop.
Okay, so the universe forbids the holes.
Right. Physicists like Stephen Hawking proposed the chronology protection conjecture, which basically argues that quantum effects will always blow up and destroy any hole or wormhole before it can form a time machine.
They use complex conformal diagrams of black holes to mathematically prove that even if you enter a region where closed time-like curves theoretically exist, the geometry of the singularity will crush you before you can ever escape back into the normal universe to cause a paradox.
The universe protects its own sanity through sheer gravity.
The universe protects its own sanity. I love that. But as we reach the end of our journey, we hit the final, insurmountable wall: quantum gravity. Klaus Kiefer's chapter highlights the ultimate final boss of theoretical physics.
Everything we've talked about today, Einstein space-time, block universes, rotating black holes, it all assumes time is a smooth geometric curve.
Mm.
But the quantum world is the exact opposite.
It's discrete, it's fuzzy, it's ruled by probability.
Exactly. The holy grail of modern physics is quantum gravity, the quest to unify Einstein's smooth relativity with the fuzzy quantum world. And Kiefer points out that the single biggest obstacle to that unification is time itself.
Because relativity and quantum mechanics treat time entirely differently.
Exactly. Relativity says time is a dynamic, squishable dimension. Quantum mechanics treats time as a rigid, external background parameter ticking away outside the experiment.
So what happens when they try to combine them?
When physicists try to smash these two theories together to describe the entire universe at a quantum level, they get equations like the famous Wheeler-DeWitt equation. And the most shocking feature of the Wheeler-DeWitt equation is that the variable t for time completely drops out of the math.
Time literally vanishes from the fundamental equation of the universe.
Yes. The wave function of the universe doesn't evolve over time. It simply exists in a timeless state of quantum probability, leaving the ultimate nature of time as the single greatest unsolved mystery in human knowledge.
So after an hour of breaking down reality, what does this all actually mean? Let's try to synthesize this massive journey. We started by looking at Newton's rigid, absolute metronome ticking away in the background.
Then we watched Einstein smash that metronome, replacing it with a flexible relative spacetime where my now is entirely different from your now.
We waded through the metaphysical war between endurantism's 3D moving slice and perdurantism's massive 4D spacetime loaf.
We saw how logicians had to literally invent multi-valued truth tables, throwing away classical logic just to keep the future undetermined and save us from fatalism.
We stared into the terrifying void of thermodynamics, realizing that the fundamental equations of the universe run forwards and backwards equally.
And we learned that the only reason eggs break, and we remember the past, is because of the past hypothesis. The fact that the Big Bang was a uniquely low entropy state, and we are just surfing the wave of increasing disorder, praying we aren't isolated Boltzmann brains hallucinating the whole thing.
We zoomed in on human consciousness, learning how our phenomenological experience of a specious present tricks us into feeling a flow of time that physics says doesn't exist.
And we found profound, ancient ethical relief in Lucretian temporal neutrality, realizing that if we don't fear the billions of years before our birth, we have absolutely no logical reason to fear the billions of years after our death.
The Oxford Handbook of Philosophy of Time is a staggering achievement because it forces us to realize that time is not merely a clock on the wall. It is an infinitely deep, interdisciplinary puzzle that requires the combined force of formal logic, evolutionary ethics, statistical thermodynamics, cognitive phenomenology, and quantum geometry to even scratch the surface.
It is the ultimate boundary of human comprehension.
To wrap up this deep dive, we want to leave you sitting there right now with a final, provocative thought, something to mull over long after this audio stops playing. It builds on a concept referenced in the text regarding the physicist Eugene Wigner and his view on quantum mechanics.
Right, Wigner held a highly controversial but deeply fascinating view. He suggested that it requires a conscious observer to collapse a quantum wave packet.
Meaning?
Before a conscious mind looks at an experiment, the universe exists in a fuzzy superposition of endless probabilities. It's only the act of observation, the act of a conscious mind interacting with reality, that forces the universe to pick a definite state.
Now, combine Wigner's idea with what we learned from the physicist Arthur Eddington, who suggested that the very direction and flow of time is heavily tied to human phenomenological experience.
If our brains are what stitch together those instantaneous retentionless snapshots to create the illusion of a flowing movie out of a static block universe.
If you take both of those ideas and push them to their absolute logical extreme, an incredible extrapolation emerges.
It's mind-blowing.
If a conscious observer is required to collapse quantum probability into hard physical reality, and if the flowing arrow of time is fundamentally reliant on the cognitive machinery of a mind perceiving it, could it be that without conscious observers, the universe wouldn't just be an empty, dark void?
Could it be that without a mind to perceive it, the universe would be entirely fundamentally timeless?
Does time create consciousness, or does consciousness create time? Think about that the next time you catch yourself staring at the ticking second hand of a wall clock. Is the clock ticking because time is passing, or is time passing simply because you are watching the clock? Thank you for taking this deep dive with us.